Hi, I'm Brad Davis, one of the authors of Oculus Rift in Action. You may also know me as Jericho if you're a frequent visitor to the Oculus forums, where I offer advice, both wanted and unwanted. My last video discussed using asynchronous time warp to improve the perceived latency of your application. While asynchronous time warp is an effective fail-safe mechanism for ensuring that your applications don't stutter if the rendering frame rate drops, it has its limitations. In the long run, you're better off ensuring that your rendering engine can meet the required frame rates. So today I'm going to talk about another method of improving your Rift application's performance, dynamic frame buffer scaling. This technique works by reducing the total number of pixels you have to render for each frame. If you develop for the Rift, you should already know that it works by rendering two views of a given scene to off-screen frame buffers, and then passes the rendered scenes into the SDK for distortion and display on the headset. You may also be aware that the off-screen frame buffers have a significantly higher resolution than the areas on the screen on which the distorted images will eventually be shown. To understand why that is, you need to understand the nature of the distortion. Here we have an example of a mesh which is alternating between a distorted and undistorted view. The triangles near the edges of the mesh get smaller in the distorted version, but near the center the triangles actually get bigger. This magnification effect is why the off-screen frame buffer must be of a higher resolution than the screen, so that at the point of greatest magnification there is a one-to-one correspondence between the source pixels in the texture and the target pixels on the screen. So the recommended texture size from the SDK is what's needed to ensure that there's no loss of image quality. But in VR, hitting your frame rate target is more important than overall image quality. That's where dynamic frame buffer scaling comes in. If you're unable to hit the frame rate, you can use it to reduce the total number of pixels you're required to render, sacrificing a little bit of image quality for a better overall experience. So how does it actually work? It works by not rendering your scene to the whole off-screen frame buffer. Typically, when handling a per-eye render, you set a Direct3D or OpenGL viewport immediately before the drawing calls, looking something like this. On each frame, you pass information about your off-screen rendering to the SDK. If you examine the SDK end frame call, you'll see that this includes the viewport to which you've rendered. If you set a smaller viewport, then you render to a smaller region of the off-screen frame buffer, and thus fewer pixels. The SDK will see the smaller viewport and will compensate its distortion code to account for it. Here we see a modified version of our rendering code. Instead of simply accepting the current viewport settings in the OVR texture structure, we're modifying the viewport on each frame by multiplying it by render scale. Render scale is a number between 0 and 1, which determines how much of the off-screen frame buffer we actually use. We set our OpenGL or Direct3D viewport to the dimensions we've determined, and then we execute our drawing calls for the scene. Let's take a look at this technique in practice. Here we have our basic test scene consisting of a skybox, a floor, and a color cube. The current texture scale is 1, so I'm using the full extent of the off-screen frame buffer. Whenever I press the N key, the texture scale will be multiplied by the inverse of the square root of 2, so the total number of pixels rendered will be halved. As I press the key for the first time, the difference to the overall scene quality is minimal, even though I'm now only rendering half as many pixels as I was before. The floor texture is slightly blurrier, and there are more pronounced moire patterns as I move my head, but the effect is still very slight. Moving down another level, I'm now rendering only a quarter of the pixels of the original frame. Here the image quality is visibly worse, but certainly not unplayable. Moving down 2 more levels, I'm now only rendering 1/16 of the original pixels. Now the effective per-eye size is something close to a 360 by 300 display, and I feel as if I've been teleported into a Doom level. Reducing image quality isn't something you ever want to do in the course of developing your application, but as you can see here, you can reduce it quite a lot before the effects become apparent to the user. If you're only missing your rendering time budget by 10%, you'll never even have to go as far as I have in my demo, and the resulting degradation can be completely imperceptible to most users. Of course, like asynchronous time warp, this technique is not a panacea. Reducing the number of pixels you render will only improve your pipeline's frame rate if you are bottlenecking on pixel shaders, frame buffer bandwidth, or texture bandwidth. As you lower the total number of pixels rendered, eventually another bottleneck will appear. Additionally, it's up to you, the app developer, to manage the render scale value in response to lower than desired frame rates. Dynamic frame buffer scaling represents an extremely easy way of compensating for lower than desired frame rates in your rendering engine. This topic will be covered in more detail in Chapter 9 of Oculus Rift in Action, linked below, and the source code for the example used can be found in the book's GitHub repository, also linked below. Thank you for watching.